There we go. So this question we started talking about, we talked about most of the details, but just to kind of recap, on Tuesday we had this situation where we had a laptop battery and we were tracking the rate at which the battery is discharged. So just by percentage charge. And we decided that in comparing this information over 40 minutes, it was a 13% decrease in terms of the percentage that was listed. So 13% over 40, however you want to list that, 0.325% charge per minute was how much it was decreasing by, and so or in decimal form that was what, 0.3, yeah, it was 0.325? Yes. 0.325 as a negative number would be that value of m that we used. So I think we stopped in the middle of this question. Suppose we next want to describe the percent battery charge and its change between time 35 and 48 in the same class period. We might have stopped kind of in the middle of this or right near the end, but quickly. So just to quickly recap, if we want to answer these questions, again, and this is similar to what you had to do in your homework, what's still coming up in upcoming homework, things that will be coming up on your test, we're just going to alter some of the context to be smaller intervals of time instead of whole class periods or several minutes long. So suppose that between time 35 and 48, so same starting point, earlier ending point, we wanted to know how much the percent charge changed. So we have this same rate of change that we're able to use because we're assuming that this is constant rate of change, that 0.325% per minute decrease corresponds to the whole class period, or at least that time period between 35 and 75 minutes. So I believe where we got to was just talking about that this was a 13-minute time interval. And so to calculate how much the battery percent charge changed, we did, oh, well, it's 13 minutes at this 0.325% per minute decrease. So over that time interval there, that's symbolically, that's our MDX, or with the letters from this problem, MDT. So we've got this approximately negative 4.225% change in the battery charge during that time interval. So if I know how much it was at the beginning and I want to know how much it was at the end, just final equals initial plus or minus the change that happens. So writing it generally as plus a change, but the change could be something negative like here. So we had the initial charge 41% minus the 4.225% it decreased during the interval to find our final value. So we don't have to know the percent charge at the beginning of class. In order to answer this, we don't have to solve for that. All we have to know is the rate of change and some place to start. So in this case, it was that 35 minutes into class. So here's one that we did not start. Let's put these little formulas up here. Still the same scenario, so the same rate. So take a couple minutes, see if you can write an expression and then also compute as much as possible. There are more symbols this time. The percent battery charge and its change between t equals 35 and some general value of t in the same class period. So imagining an interval that ends at t instead of one that ends at time 48 or something like that. So in this case, an interval between time 35 and some general t, time in the future, what would be an expression that we can write for dt? The variation in the amount of time, or the amount of elapsed time between time 35 and something mysterious. Yeah? Oh, yeah, so t minus 35. Good job, team effort. Yeah, t minus 35, so final minus initial, right? If you need to find a change and you have a beginning and an ending value, you can just subtract. Now, if I want to find a change in p, the variation in the percentage charge during this general interval, do I have a final and initial already? I have an initial, but I don't know what the final is. That's kind of the problem. Since I don't know the percent charge at a general time t, and that's kind of my task here, to find p final, since p and t are related, to find that change, instead of doing final minus initial, remember that p and t are related by this constant rate. So our trick is to use our constant rate of change. If I know how much t has varied by, then the amount that p is varied by is going to be a constant multiple of that. What's the number that we multiply by? Yeah, negative 0.325, right? That percent change per minute for t minus 35 minutes. So symbolically, generically, we can talk about final minus initial for a change in t, or an amount of elapsed time since whatever time we're interested in this case from 35 to something mysterious. So the amount of elapsed time during that interval, final minus initial. Since we don't have a final percent charge for a general t, we just have one for the end of class at 75 minutes, we don't want to just say, oh, the 75, whatever it was, 28% at the end, because that doesn't apply to any t, that only applies to t equals 75. So I want to do, instead of final minus initial, I'll use the top relationship there, the change in percentage battery charge, or the variation that the battery charge goes through during an interval of time, is a multiple of that length of the interval of the time that we're interested in. So number-wise, negative 0.325 times the dt that we just found, t minus 35. But then, since we have this expression, although it's not a number right now, it's an expression in terms of any time t, that means I can write an expression for p final, final being not necessarily the end of class, but the end being at mystery time t, any time t that I choose, as long as it's in this class period with the same charge starting your battery, etc. I just need my initial value, the initial value of the percent battery charge, plus, or in this case minus, the amount of change that we had. So our initial value was that 41%, and then instead of subtracting 0.325 times 13 minutes like the last problem, it's 0.325 times whatever t minus 35 is. So we have a general expression that would be valid for a variety of values of t. And we don't have to do a different computation for every different value of t. I don't have to find mysterious points at time 0 in order to be able to answer this. All I have to know is any point and the rate of change. And what I've got is some initial value, this time 35, that corresponds to a percent battery charge of 41, and then the rate at which it decreases by having had a second reference point. I saw a question a minute ago. Okay. All right, so in terms of this, I know someone asked for a similar expression on Tuesday. Do we need to simplify that, like get rid of the parentheses? You can if you want to. You don't need to. And in fact, by leaving it in this format, you can see the construction of this formula, where these numbers come from, instead of just seeing some random decimal numbers thrown together. But if you keep in mind what this is a constant rate of change situation. I've got an initial value plus change. And I've got a constant multiple of a subtraction problem, that constant multiple being that constant rate of change, and the subtraction problem being how much time has elapsed. And I can allow t to take on any value that is valid for this question. So anything that seems reasonable, I could let it be 50 minutes into the class period, 68.2 minutes into the class period, and evaluate this. or I could just leave this as a general expression for constant rate of change. So, questions about the symbols or computations? What if I picked a t value that's less than 35? So what if I picked t is 20? I guess it depends on if you were actually using your laptop earlier in the class period, whether that would make any sense. But at time 20, I would just be going backward. If you'd had your laptop open or using it the same way for the full class period, where it had actually been decreasing for a while before it got to this time 35, 41% charge, this would actually be okay. Would this formula still give us something that seems reasonable? If I had like t equals 20 in this spot here, yeah, if I put t equals 20, I get negative 15. So 15 minutes ago, a negative 15 times a negative rate of change, that would give me a positive result, or my result would end up being larger than 41 in the end, which should seem reasonable. Just imagining, well, right now, I know at a certain point in time, and let's see if I can get this to, oh, I didn't even turn it on yet. If I had a certain point in time, I had a known charge and I know it decreases from there. If I go back, not too far maybe, if I go back not too far, certainly probably not past the beginning of class, time 0 for sure, maybe the charge would be higher and higher, meaning indicating if I were only going forward in time through the class period, it's decreasing at the same rate all the time. Now, we don't actually know whether that's true or not, so you have to be careful if you're using a formula during an interval where it's not specified that it necessarily works or that it applies, but it seems kind of reasonable that at least between 0 and 75, that you could maybe have the same rate taking place, the same rate of change in the percent battery charge with respect to minutes of time gone by. All right, so we're going to change gears a little bit, not too much. Still talking about constant rate of change, but as I said, we're actually going to use this concept for the whole class, despite the fact that not everything changes with a constant rate all the time. There are lots of things that don't change with a constant rate all the time. On your way here, whether you're walking on a skateboard, driving, whatever you're doing, you probably didn't go one constant speed the whole time. You have to speed up, slow down, but nonetheless, you manage to make it whatever distance in some amount of time. And at various points along your route, we could measure how far you are from where you started or how far you are from your goal of getting here, and talk about maybe your speed over the last 10 seconds when you didn't have to slow down to avoid hitting someone, or you didn't have to like cut across a sidewalk that had 10 million people on it simultaneously. So if there's some interval of time where you're going a constant rate, we can still measure your progress during that time. Or if it's essentially a constant rate, if it's close enough to a constant rate, we can look at just little pieces at a time and piece together all the puzzle parts to make your whole journey from home or wherever you were previously to class today. Now, I'm going to take a look at something that's a little bit more fast-moving than you on your way to class today, or anyone on their way to class. But let me pull this up. All right, so here we have Usain Bolt, who is much faster than the rest of us. All right, I don't know if there's going to be sound or not, but in any case, running as fast as you possibly can, much faster than I possibly can. This is from 2014, does it say on there? But set a world record for the 100-meter race, running very fast at first. At this point, he's not running as fast anymore. During the race, he's running probably as fast as he can. Now, that guy's trying to keep up with him and can hardly do it even when he's in his cool-down phase. But here is a graph. I'm going to pause it at the end here. 9.58 seconds. There we go. This is a graph of his speed, measured not by measuring his speed. He didn't come with a speedometer, but by measuring his position. Or this is a graph of his position, but you can measure his speed. This is a graph of him starting at the starting line, and as time goes on, up to 9.58 seconds, his distance goes up to 100 meters. So this graph was created by having a bunch of data where he was at a whole bunch of points in time during the race, and then piecing them together, modeling it with a polynomial function in this case. If you want to see what the function is. Let's see. Here it is. We've got a 5th degree polynomial function where this is a portion of it. Computers can do all sorts of cool things, give it some data points, and we can get functions that go through the points that you give it. And in this case, as you could see, when he was running, he wasn't like running super fast and then stopping and then speeding up and doing crazy. He was going pretty much, if you just look at it, obviously at the start, he had to start from nothing, from not running to running. So he wasn't going one speed the full time. But after a few seconds, if he could have sped up, he would. He would probably have assumed to preferred to have like run faster and faster and faster and faster. But at some point in time, you just can't. And it looks like, if you look at this doesn't look at the beginning very close to a line. But throughout this, like, I'm just going to say 3 seconds to, let's see the end of this again. 3 seconds to maybe about here, 9 seconds or so, looks pretty constant, right? It looks pretty much like a straight line. Now we could zoom in and see, and clearly this was a polynomial. This is not actually a straight line in any part of it, but zoomed to certain levels and even just seeing 10 seconds at a time, a lot of this looks very close to linear, which means if we have something that looks like a line, that means that what we're seeing is something where the proportion of visually vertical to horizontal changes, or conceptually in this case, the ratio of distance to time elapsed, distance run during a little interval to time elapsed, stays pretty consistent. So that would indicate we've got a fairly constant rate of change. Now over the whole time, no, certainly not down here. This isn't what lines do. And in reality, I know that it's this crazy graph here, negative 0.002 t to the 5th and all this. That is a very small coefficient on that. So there's a lot of other stuff going on in this formula, but the end result matches his positions. And so as he gets farther and farther from the starting line, at the beginning I can see this is about, let's see if I can get it to 2.01. After 2.01 seconds, let me click on this. 2.01 seconds, he's 11.4 meters from the starting line. If you can see the coordinates up in that upper corner. So if he'd been running the same speed for those 2 seconds, it would have been about, what, 5.5, 5 3/4 meters per second. Now, this is the time interval where it looks least like a straight line from a distance here. That doesn't look too straight at all. But what if I look in closer? So I'm going to try to not click on this axis here. I'm going to have to drag this out here. If I were to look in a little bit closer, let's say I look between, this is everything between 0 and 1 second. There we go. You can see it's still not a straight line. And it's never going to be exactly a straight line, but you can zoom in to make it look straighter and straighter. Like at this point, between 0.6 and 1, that looks pretty straight. Just judging it, like if I were to graph a straight line that went from here, if I can click on this, there we go, to there, I probably couldn't tell the difference between my straight line and that 5th degree polynomial. They look fairly even. Now this part from 0 to there looks less so, or 0 to the first half second doesn't quite look like a straight line. But let's see, if I'm at this 0.6 and 1.4, that means after 0.6 of a second, he's run 1.4 meters. If I look at time 1, he's gone about 3.5 meters. I could judge saying, well, it's probably pretty close, just doing standard linear computations that you learned long ago. So like, well, during this 0.4 of a second between 0.6 and 1, I could maybe judge what his speed is. Let me get this doodad on pretty closely. So if I have this point, I'll just write out the things here so I can move. 1, 3.5, just rounding off. After 1 second, he's gone 3.5 meters, whereas after, what, 0.6 seconds, he'd run, what was it, 1.43? Yeah, after 0.6 seconds, about 1.43 meters. So during that 0.4 of a second, that section of the graph looks fairly linear. I said, well, maybe he was running during that 0.4 of a second at approximately a constant rate of change, a constant speed of, let's see, well, 3.5 minus 1.43 sounds like about 2.07 meters that he ran in 0.4 seconds. So if I wanted to, this would be an average rate of change computation that I'm doing, but this average rate of change is very close to an actual constant rate of change during the interval, because this is very close to, as you can see, just looking the same all across. I could check by picking a point in the middle and seeing if that y value in the middle is kind of halfway between 1.43 and 3.5. 2.07 divided by 0.4. 0.5, let's see now, 5 point, I don't want to turn off my pen thing and have it misbehave again, but what about 5.75? Is that what that is? Meters per second? 27, oh, 5.175. So about 5.175 meters per second there, or between 0 and 0.6, if that were a constant rate, which it looks less so. I could say, oh, well, it's probably slower. He's going slower. So visually, if you're looking for slower and faster in this graph, it's steeper and less steep. But numerically speaking, you're looking for the ratio of the changes between vertical and horizontal that you can see visually, or like the y's and the x's, which represent its distance and time. But again, we're zoomed into a very small portion. This is just the first second of the graph. What I'm going to have you do on Tuesday in class, we're going to do some explorations and play around with, I'm going to give you a file that has some of this information in it, and you're going to get a chance to draw some points and explore some small changes and see what all we can make happen using some trickiness in GC. I just want to have some more of you have some time to work with GC, get some recitation feedback and so forth. But just zooming back out here, there we go. Let's see. This is the one I'm looking for. Let's just move this out of the way a little bit. There we go. So you can see, and here, let me zoom it the other direction if I can find the right button. There we go. So at the beginning, just looking at this, talking about what's happening, he's going slowly at first and then more quickly later on. And we can tell that by the kind of like the angle of the graph, not like 45 degrees or 23 degrees, that sort of angle, but just steepness of the graph. So things that aren't linear functions, as long as they're relatively smooth, like they don't have jagged points, weird star-shaped things, we can talk about rates of change by looking for small pieces, at least small-ish pieces, where there seems to be an approximately constant rate of change, whether that involves looking at, in this case, maybe a few seconds at a time or a half a second at a time, or maybe, I mean, time doesn't have to be the independent variable, but if it is, maybe it'd need to be down to the thousandth of a second at a time, or at least to be more accurate about it, because maybe those changes are happening, the changes in speed, the changes at which the distance increases related to the time. Maybe that is changing more rapidly. Not with him, because he kind of reached this peak speed and then just kept going, but where is this? Oh, it zoomed back out on me. So like this part right here just looks like, okay, trucking along, uphill, 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 but it seems pretty much the same angle for a good portion of this. What we're gonna do on, like I said, on Tuesday, I'll get you a worksheet along with a GC file worksheet just to copy stuff down so you can write it more easily instead of switching back and forth between windows. But we'll have the actual formula in a GC file so you can get XY points. We can use this to make computations, determine constant rates at various small intervals of time throughout. And then we'll talk about what that means about how we could estimate tracking the distance traveled from that. Now, in reality, we know that's actually where we started from. We actually started from knowing that he ran this 100 meters and we had his positions at a bunch of times and we can get rates from that. But our goal for this first half of the class really is to be able to use constant rates and say what happens because of that. So what we're going to be starting to do is, although we actually know what happens because of it, so starting from something where there's a known end result, we're going to use Usain Bolt, because might as well, to talk about how change happens when we have relatively constant rates of change, how we can use those even if they vary from interval to interval, or from one time frame to another, how we can use those to see, in this case, how far he ran. And we can come up with an estimate that probably won't be exactly 100 meters, but it should be relatively close if we have good estimates of his speed at times when it matters, at times when it's changing the most, and at using those rates when it isn't changing very much for longer periods of time and saving ourselves some work. But what we're building up to is, after next Tuesday, we're going to be starting from knowing information instead of knowing like the distance, what happened. We're going to be looking at graphs that indicate rates and using these graphs of rates to try to determine what happens because of them. So it's as if you have a graph of looking at a speedometer, for instance, and saying, oh, well, it was 45 and then went to 65 and then went back down, and when did it make all these changes? And how do we know how far you drove based on just knowing those rates and not knowing the distances ahead of time? And again, it's not all distances and times, but just to relate it to what we're looking at. So as a means to get to that, and I'll just use Usain Bolt as an example, although, like I said, we'll get back to him in detail, we'll get back to him on Tuesday. But let's see if I can click on this. There we go. So the picture that we saw, if you ran this 100 meters in 9.58 seconds, and you're just asked the question, how fast did he run? Keep in mind that that's not, he didn't actually run one rate the whole time. He would have liked to. I'm sure he would have liked to start out instantaneously at top human speed possible. Not quite possible, but he did it pretty close. So we can answer a question by saying, well, his average speed over this 9.58 seconds is, well, how would you find that? You want to find his average speed, how fast he was going, if he was going the same speed that whole time. Yeah, just divide meters by seconds. So 100 meters divided by 9.58 seconds is going to be more than 10, like 11 point something probably. Now keep in mind, we did a short computation, came up with 5 point something and 6 point something for speed in meters per second near the beginning of the race. So we must have been going faster later on. But this question, if we want to talk about a speed based on that, all we could do is an average speed over that 9.58 seconds, if that's the only information we have. But we already talked about this. Did he run at a constant speed? No. So if after 1 second we saw this point on the graph, we knew what his speed was at that time. This isn't a computation that we did. We said like, well, over the time 0.6 to time 1, we could find his average speed over that interval. But, you know, like if you're driving, you can look and say, how fast am I going now? And you don't have to like subtract and divide to get a how fast you're going. That would make for an awful lot of car accidents. But if you have something like this, it said, what would it mean that he's running at 6.148 meters per second after 1 second? It's like, well, this here's a picture 1 second into the race, move this out of the way a little bit. So this is 1 second into the race. How fast is he running? Well, it says 6.148 meters per second, which sounds pretty fast, but it looks to me like I'm running the exact same speed as he is. I'm just less blurry, right? But he's not moving in that picture. I'm not moving too much. So if you freeze time and talk about just one value of time, we can't really talk about speed. In order to talk about speed, something has to happen. You have to have a ratio of changes between distance run and time elapsed. So maybe like let 1,000th of a second go by, and imagine just using that little fraction of a second to measure how far he went. And then we can say, okay, so he probably didn't change speeds over 1,000th of a second. So let's assume that it was constant over that. We talk about speed at a particular point in time, but in order to have speed, in order to be moving, something has to be happening. Time goes by and distance has to have happened. Because if time goes by and you didn't move, then your speed is 0. If no time goes by, then you can't move either unless you're magic. So you also don't have a speed. So when we're talking about speed, and we always talk about it like, okay, what was the speed at this point in time, at this point in time, an instantaneous speed. We can't really have that. We can have the idea of it, but in order to come up with a value, we have to imagine a little bit of time going by, so we have two numbers to compare. Just kind of like the algebra issue of, can you find a slope between a point and itself? No, you have to have two separate points. They could be close together, and that's kind of our key here. But how we're going to describe this thing, and you'll see the book uses terminology, just altering this question a little bit. If I think about, I'm going to use the word moment to describe this. If you think of moments, like, okay, it's not an instant, which is like a spot, but a moment like a small, little interval of time. When 1 second's elapsed, if I want to talk about how fast he's running in this moment, so you can imagine maybe that like 1,000th of a second going by. If I have a little bit of time, I can compute a speed if I have positions. So in terms of just terminology-wise, you'll see this term moment thrown around. It's just used to indicate a small interval, one of these small intervals that we need to have in order to be able to talk about rates and rates of change. So if I'm talking about this at 6.148 meters per second, in order to measure that rate, maybe I'd really look between 6.148 and 6.149, or that's the speed, sorry, at about 1 second, 1 and 1.001 seconds into the race. I'm like, okay, so during that time, he ran a little tiny bit, went forward a very small distance, but if I take that very small distance and divide it by my very small time, it happens to come out to 6.148, meaning during any increment of time, this little 1,000th of a second, the distance traveled is 6.148 times as much. Our same meaning of distance, or same meaning of rate with time and distance here as we've used for using this rate in other situations. But just instead of thinking about long intervals of time, we're going to talk about just small intervals of time. So you think of this moment as a small interval of values of the independent variable, whether it's time or something else, just as x increases a small amount. Or if we look at just a small interval of time and imagine a change, a dx, that's very small, then we can assume that, unless it's a crazy function, and there are some exceptions, there's a whole section in your book about things that don't have constant rates of change anywhere, that aren't essentially constant anywhere. There are weird things like that, but people running isn't one of those situations. So we're going to use dx, just as before, but in order to be able to use it in more situations, what we're going to be using it on from now on, I mean, it's still valid for constant rates of change. This dx, a change in the independent variable, can be any size you want, because within the domain, your dependent variable is always changing at the same rate with respect to the independent variable. In situations that don't overall have one constant rate of change, though, we want to restrict ourselves to only looking at small moments at a time and talking about dx within those small moments, like within a small moment between time 1 and time 1.001. We'll let dx take on little values there and calculate accumulations in distance from the starting line, little additional distances. Now, is this very tedious to do manually? Yes, it is. So we're not going to do a lot of computations. We're going to write out expressions instead, because we don't want to deal with substituting in, even using a calculator, substituting in a bunch of different values that are 1,000th or 1/10,000th of a unit apart into the same function relationship and finding all those different values and seeing what happens. It's very, very tedious. What we're going to do instead is just explain generally using our same notation, knowing our same constant rate of change relationships. We're going to use those to be able to set up our whole process. So meaning, well, for the first millionth of a second, here's what his rate of change was. And I'll use that a little bit. How far did he run during that first millionth of a second? Then the second millionth of a second, and the third millionth of a second, and so on, and append those all together to find total distance accumulated. But it's just different rates for each interval potentially, but the same process all the time. So we just have a whole bunch of small rate times time computations to add together. So that's kind of nice. It's very repetitive. Repetitive is good for things if you want to compute, use a computer. Or if you're using notation, we're going to use some math shortcut notation to indicate doing the same computation repeatedly with just slightly different numbers plugged in, like summations. All right, but in any case, rate of change at a moment, where we're talking about rate of change in these small moments, only happens if, visually speaking, if you can zoom in and it looks essentially linear. If you've got something like the sharp corner point of an absolute value function, or whatever some sort of cusp where something turns around suddenly, no matter how close you zoom in on a corner, it's never going to look not like a corner. So there are examples of places where constant rates of change or essentially constant rates of change can't exist, but they're usually individual points and don't happen in a lot of standard normal situations. So this constant rate here is the speed at the moment 1 second into the race. Now, so here's what I was saying. So I've used dx in constant rate of change situations, and it could just talk about variation in the independent variable, whatever size we wanted to, starting from anywhere, going to anywhere else in the same situation. If you have one rate that applies to the whole situation, that's great. If you don't, you have to be careful. So to use this dx and our constant rate of change notation in more places, we're going to use dx as just a small variation within moments at a time. So I can pick a size of a moment that seems to be good enough, like 1,000th of a second, and then just think about varying x within each of those individual moments from the beginning of it to the end, 0 to however large this moment is, to get a little bit of accumulation, a piece at a time. So what I was just saying, to use this constant rate of change and all of our symbols in a new situation, we'll just, when we don't have one constant rate of change that applies everywhere, we're just going to use this dx to represent very small increments of change within each interval, where we decide, okay, these are small enough so that within each one, it looks like we have, or it seems close enough to, constant rate of change. And this close enough to is kind of a weird concept, like don't I want to have something more exact than close enough? But in all sorts of science, there's always some sort of tolerance level past which you can't distinguish between two things, or it doesn't matter because it's close enough, like having parts fit together. If you're constructing physical metal parts that need to screw together, there's going to be a little tiny variation in their size. As long as it's not too much, it still works, right? If one thing's too big or the other's too small, it's not going to fit together at all, or might be too loose and fall apart. But there's always this idea of, with physical constructions, that there's a certain amount of tolerance in the sizes or in the measurements that is perfectly okay, or visually speaking, even with graphs that are indistinguishable from one another at a level that is close enough so that it doesn't have any impact on the final result. Although we will talk about how to make this better and better and better in perpetuity, so that in essence we do have an exact result by the end. So this dx, I don't know if I used this word earlier or not, but it's generally called a differential only when we're talking about this in small moments, but we can always use it to represent a change in x or a variation in x. When we use this differential, the use of this word differential or the symbol dx, either one, indicates that we're talking about constant rate of change. So if you see this dx or dy or d whatever letter it is, talking about those, you need to know what symbols are being used for independent and dependent. If it's not x and y, those will be defined. But when you see these, they imply that there's a constant rate of change, at least within moments. And the term differential generally refers to just very small moments at a time that we're talking about change within. But we can use it in larger situations when we have constant rate of change throughout a situation also. So dy, as always, will be a constant multiple of dx as it varies. But if we want to look at another moment when there's a different constant rate of change, we'll just let dx start to vary all over again. And we can append one set of change to another and accumulate as we go. Within a moment, sorry. Don't know how that ended up on the second line. So let's go back to Usain Bolt. So function f that we had before, this is the same function that I had on GC. This measures his distance from the starting line with y based on independent variable t for time, or I guess I used x here, x equals 1. X equals 1 second. So this is that small snippet that we were kind of looking at before. Between 0 and 1 second, goes a little bit past 1 second here. And you can see that, if I were to zoom in a little closer, right around 1 second, like from a distance, certainly right around 0, it's not a straight line. If I look around where that 1 is, it looks straighter, as in it's not curving quite so much. But you can see if you zoom in quite close, we've got something that looks essentially linear. So reading the numbers that we've got here, looks essentially linear from 0.99 seconds to 1.01 seconds. So we're going to imagine x varying from 1 to 1.006, just a tiny bit of variation within this moment. So in this moment that extends from the left to the right here, so 0.002 seconds from left to right, or 0.02? 0.02 seconds from left to right. This all looks pretty linear. So if I think about a time that's about 1 second into the race and go forward just a little bit, 0.006 seconds, within this larger moment, during that small interval, right closer to 1, I should be able to assume a constant rate of change. So if I want to find that constant rate of change, we've got some numbers up here. I don't actually need you to do computations with them, but just thinking about, oh, well, within this moment, it looks like an essentially constant rate of change for that whole 200th of a second. So for 6 thousandths of a second in the middle of that, that should be perfectly fine. I can measure constant rate of change, just vertical change over horizontal, change in distance, distance traveled, divided by time elapsed, change in time. Just standard algebra computations, we're just using them on a small scale in places where they wouldn't make sense on a larger scale. So, click someplace else, so that goes away. There we go. So you can see as we just look for 6 thousandths of a second, starting at time 1 and going forward a little bit within this moment, this larger moment where everything looks like a nice linear constant rate of change equation. I say, oh, well, his speed is probably 1 speed throughout that, or I can imagine that his distance from the starting line is increasing at a constant rate with respect to the time that's elapsed. Although it's not very much time elapsed, it's still going to be that constant multiple within this whole moment, but certainly within this small interval that we're showing over and over too. So let's go back and think about, and let me get my writing thing back on, so I moved it out of the way. Let's go back and think about symbols and values also in this case. So thinking about initial value of the independent and dependent variables, the differentials in x and y, the moment, it's not a symbol for that, but we're going to list out the values of these also, and the rate of change in this moment. So think about maybe first the symbols, symbolically, and then on the left, the values for these, for this specific section, for this specific example, meaning as x varies from 1 second to 1.006 seconds. His distance increases from 3.4882 to 3.5251, and asks what's his speed, but just think about the questions in this chart. How would I represent symbolically, or what's the value of each of these 6 things? Same symbols as we've had before. Just weird numbers. Not everything's nice round numbers, unfortunately, in life. All right, so looking at this motion here, what could I call as a symbol the initial value for the independent variable? So independent variable, the letter is generally x. So if I want to indicate the initial value, yeah, x sub I. Oops, this is going to misbehave on me again. So x sub I. What about the initial value of the dependent variable? Y sub I. And those are up here someplace. So initial value of x and initial value of y, the dependent variable. Or, yeah, I guess it's f is the name of the function. So those values are up there, 1 and 3.4882. What about the differential in x? I can call that dx. What's the value of that? As x varies from 1 second to 1.006 seconds. Right, so this differential is just, yeah, it's that final minus initial in terms of value, dx or x final minus x initial. But yeah, it's this value-wise, it's 0.006. Or in this graph here, it's the distance between initial and final. I think this is stopped slightly before 0.006. But this is our dx being represented here. It increases from 0 through 0.006 within this interval. And then, again, as that time goes by, the vertical change here, our differential in y, the variation in the distance from the start, changes by something also. Not very nice numbers. Here's y final. But I can do y final minus y initial and find dy, because I do have both of them, which is good because we didn't know the m. If I knew x final minus x initial times m, I could get the change in y, but I don't know m. That's the whole problem here. We don't know how fast he's going. So we've got an initial value of x and a final value of x, along with the y values, give us these 2 coordinated points, or 2 correspondence points. The change in x as it travels from one to the other is represented here, and the change in the y value. Sometimes when the function is called f, sometimes you'll see written in books df, but it's really df of x. because f of x is the dependent variable, f is just the function name. So I'll just use dy, although I think one of the later graphs shows an f mysteriously. But the differential in y is this as a symbol, but final minus initial. These two subtracted, let's see, 251 and 118. What does this come out to be? 0.0366. 9? All right, yeah. 0.0369. Is that right? Okay. So this is units on these. This 0.006, that's a time of, during this, as dx increased, we let it increase by 0.006 seconds, or we let 0.006 of a second elapse. And during that time, this is a number of meters. So apparently he ran 3.69 centimeters. This is a number of meters that went by. So if I want to talk about the rate of change in this moment, we could talk about m or dy dx, dy over dx, change in y divided by change in x, change in the dependent per change in the independent. It's that ratio of changes that you can see that this is going to be not a small number, right? We've got two small numbers, but we have to divide them. What does this come out to be approximately? 2 point something, 3 point something? 6.15? All right, so about 6.15. And this rate would be measured in, just using the natural rates here, unless we wanted to change to centimeters or something, but this is meters per second. So that's pretty darn fast. 6 point something meters per second. It's like from there to there. Now, did he actually go 6 point something meters in a whole second? No, we were just looking at 6,000ths of a second. So during that point in time, he was going this speed. Just like, to go 60 miles an hour, you don't have to drive a whole hour before it's valid, nor do you have to wait that long, or else nobody would be caught for speeding ever. But we can measure speed by using small increments of time and use whatever units of time and distance that we want to. So as for the moment part that I skipped over, there's not a symbol for it. If I want to talk about where is the moment, see, this whole second graph here is kind of representative of our, well, the moment and the changes within it. The moment is really an increment of the independent variable that we let dx vary through. So this is kind of arbitrary. You don't have to define it precisely, but this moment is just picking an interval where it seems like we have, or it is close enough to, a constant rate of change. So this moment extends from 0.99 to 1.01 approximately, and I could list that as an interval. 0.99, just to explain to somebody else where I was looking in the graph to see something that made it look like constant rate of change. But it's kind of a vague, we looked around 1 second. As long as you just realize that the values of dx, we let dx vary from 0 up to 0.006. That doesn't mean that we have just a moment of 0.006. We were looking at a larger area than that and happened to see that throughout that we can use any portion of this. Like we could have worked back here, and we'd probably find a very similar rate of change, about 6.15 within like the earlier part of this moment that's displayed, or within the later part that's displayed. So a moment is just, it's kind of a vague concept. It's just pick a small interval, but then let x vary within that interval. And you can start, as if this was our whole situation from our constant rate of change. Within this moment, I can start variation from anywhere and continue throughout as big as the whole moment is, and I should get similar, if not exactly the same down to level of accuracy of our decimals in the first place, constant rates of change. All right, so next time we'll be working on actually doing some computations. We'll use GC. You'll get to create some formulas that do this sort of computation.